All right, today we're going to talk about complex and imaginary numbers. Okay, I want to start out by taking a look at the square root of 4, and it's equal to 2. And the reason it's equal to 2 is because this number 2 times itself equals 4. Okay, so we say square root of 4 is 2 because 2 times 2 is 4. Now, I will go ahead and mention that this sign indicates the principal square root of 4, but we know that negative 2 times itself will also give us positive 4, so it qualifies as a square root of 4 as well. Now, what we're interested in now is finding the square root of negative 4. Now, since we've used 2 and negative 2 as answers for the square root of positive 4, then we don't have any numbers that will actually do this, and really it's a sign problem for us. We can't find a number whose sign times itself is equal to negative, because positive times positive, positive, and negative times negative is negative. Okay, so because this is impossible, we invent a number called I, whose value is I equals the square root of negative 1, or its characteristic. Thus, when you square both sides of this equation, you get I squared on the left-hand side, and when you square a square root, of course, they're inverse operations. They cancel each other, so we end up with I squared is equal to negative 1. All right, so when we run up on a problem like the square root of negative 4, now we have a solution. We can factor it into 4 times negative 1. Using a property of radicals, we then break it up into the square root of 4 times the square root of negative 1. Square root of 4 yields 2, and then the square root of negative 1 by definition is I, so the square root of negative 4 is 2I. And go ahead and try this one. Okay, square root of 9 is 3, and of course the negative gives us the I, and that would be 3I would be our answer. Okay, so here we've got a little chart of the powers of I, and we've already stated that I is equal to the square root of negative 1, and then if we square both sides of this, of course we get I squared is equal to, that's a big square there, I squared is equal to negative 1. Now, if we want to find the value for I to the third power, well then if we just simply use what we've already got, I times I squared, and we use these two answers, well that gives us negative 1 times I, because the square root of negative I squared is negative 1, and negative 1 times I is negative I, and that's how we get this negative I. And then if we work with I to the fourth, why of course we can break that into I squared times I squared. When you multiply like bases, you add their exponents. That would give you I to the fourth. Our value for I squared we've established is negative 1, so we have negative 1 times negative 1, which gives us positive 1. Now, I to the fourth is a very useful tool for us in simplifying powers of I. And so how could we look at I to the fifth? Why, we're going to use I to the fourth, and so we get I times 1, or simply I. I to the sixth could be I to the fourth times I squared, which is going to be 1 times negative 1, or gives us negative 1. I to the seventh, well, we're going to break it down into I to the fourth times I cubed, which is 1 times, well, we already have established what I cubed is, 1 times negative I, and of course that gives us negative I. And then I to the eighth, well, just 2I to the fourth, and that's going to be 1 times 1, or 1. Now, as you see, I to the first is I squared negative 1, I to the third negative I to the fourth positive 1, I to the fifth I, negative 1, negative I, and positive 1. And see, we're just kind of cycling through these these four values, I, negative 1, negative I, and positive 1. Okay, so now remember I said that the key to simplifying any power of I is going to be I to the fourth. So when we want to find I to any power, what we're interested in doing is we're looking at breaking it down into the largest multiple of 4 that is less than whatever we have. Okay, so multiple 4s are 4, 8, 12, 16, 20, 24. 24 is bigger than 23, so 20 is the largest multiple of 4 that's less than 23. So I'm going to write the I to the 23rd as I to the 20th times I cubed. Again, when you multiply like bases, you're adding the exponent. So I can break 23rd into 20 times 3. And of course, I to the 20th is just going to be a bunch of I to the 4th. If you just want to imagine, you got I to the 4th times I to the 4th times I to the 4th times there's I to the 4th. There's 5 of these, right? 4, 8, 12, 16, 20. Each one turns out to equal 1, and then all those 1's times together just give you 1. So I to the 20th is 1, and it's so when you have a factor of positive 1 in a product, it disappears into the answer. So 1 times I cubed is I cubed, and from the chart, I cubed equals negative I. All right, go ahead and find the what I to the 77th power is. Okay, so the largest multiple of 4 that's less than 77 is 76. So we're going to break I to the 77th into I to the 76 times I, or I to the 1st if you want to put the I to the 1st in there. All those 19 I to the 4th, so times 1 times itself 19 times, still going to give you just 1, and 1 times I is I, so it's going to be, the answer is I. All right? Okay. Well, now we're going to use it in solving equations, and in previous lessons we've talked about how to solve quadratic equations when the linear term or the x to the first term is not present. Well, as you can see in this equation, it has x squared, so it qualifies to be quadratic, but I don't see any x to the first. When this is the case, our strategy for solving this is just like solving linear equations. We want to isolate the variable, or isolate the x squared term. So if we want to get the x squared term by itself, we'll start by subtracting 10 from both sides, so I'll do that. And that's going to give me 3x squared equals negative 36. It's still not by itself, got to divide by 3. And I get x squared is equal to negative 12. Now, the way you get rid of squared is taking the square root of both sides, and we know that when we use the square root as an operation, on the side that has the numbers, not the variable side, we preface it with a plus or minus. We're responsible for positive and negative roots. And this time we'll break 12 down into 3 factors. I'll break it down into negative 1 because of the negative, times the square root of 4, times the square root of 3. Again, to simplify radicals or square roots, we want to find the largest perfect square factor of the number and then show it as that as times whatever's left, and of course what's left here is 3. So putting these in the correct order, or the preferred order, is going to be, what's the square root of 4? That's going to be 2. So we're going to put 2 first. Next, square root of negative 1, of course that's I, and then the square root of 3 at the end. This is my preferred order for my students. I want the I in front of the square root. Okay? Plus or minus 2I square root of 3. Try this one. Okay. Should have gotten plus or minus 3I square root of 2. Quickly going through the steps, we'll isolate the x squared. We'll subtract 26 from both sides. We get negative 36 on this side, 2x squared on this side. Divide by the 2 to get x squared by itself. We get x squared is equal to negative 18. To get rid of the square, we take the square root of both sides. That's going to give us x on this side. Should have put the plus or minus in up here. And then negative is negative 1, and 18 is broken down into the perfect square factor 9 and 2. Square root of 9 is 3. Square root of negative 1 is I. Square root of 2. Okay, let's take a look at another one here. This time the x is not squared, but the parentheses that x is inside of is squared, and we just do it the same way as we've done the last problem. We're going to isolate what's being squared, and here it's a parentheses, not just the variable. So for starters, we need to get rid of this negative 8. Negative 1/8, so I'm going to multiply by the reciprocal, negative 8 over 1. Well, over here I'll just write it as negative 8 because I'm not dealing with a fraction. And we know that the 8's will cancel and the 1's will cancel, and negative times negative is positive. That gives us x plus 3 squared is equal to negative 56. Okay, just like always, to get rid of squared, we take square root of both sides. Square and square root cancel each other. They're inverse operations. We get x plus 3 on this side. We start with plus or minus. And let's see, I think this is going to be negative 1 times 4 times 14. I think the largest perfect square factor in 56 is 14. So we've got the square root of all of those, and it's going to be 2i square root of 14. Now, 14 couldn't be broken down into 2 times 7, but it doesn't take us anywhere because neither 2 or 7 are perfect squares. They don't come out from underneath the radical, so we wouldn't do that. But the only problem we have left is x is not by itself. So we got to get rid of that plus 3, and we'll do it by subtracting 3 from both sides. And my preference for my students is that you put that minus 3 in front of the plus or minus sign. Okay, so we get x is equal to negative 3 plus or minus 2i square root of 14. Okay, now let's understand this answer right here. With this plus or minus sign, this really means two answers. It means x is equal to negative 3 plus 2i square root of 14, and also x is equal to negative 3 minus 2i square root of 14. Now for my class, I'll accept that answer right there, but you need to understand that this is really two answers. Okay? You try this one. All right. Well, you should have gotten x equals negative 1 plus or minus I square root of 10. Moving through this really quickly, what did we do? We times both sides by negative 2. On this side I wrote as negative 2 over 1, the reciprocal of this. Reciprocals cancel. You get 1. On this side I just times it by negative 2. So I got plus x plus 1 in parentheses squared equals negative 10. I took the square root of both sides. X plus 1 is equal to plus or minus, and then I went ahead and took the negative 1 out of the negative 10 and broke this down into negative 1 times 10. Negative 1 was I. Square root of 10 doesn't simplify. We subtract 1 from both sides. That gives us our answer. All right, I want to talk to you about complex numbers, and I sort of left imaginary numbers off of this, but let's just talk about complex numbers first. A complex number is a number that's really a binomial. It's a plus bi, where I is that imaginary unit, where a is the real part and b times I, is the imaginary part. Okay. Now here we're showing how to add complex numbers. We usually write them as binomials, so there'll be parentheses around them. And the rules in algebra for a plus between parentheses is to drop parentheses and add like terms. So that's exactly what we do. We take the 4 and we add the 3 to it, and that gives us the 7 here. And then the negative I plus a positive 2i is going to give us positive 1i, and of course we don't have to write the 1 in here. So go ahead and work this one out. Okay, coming back to you now, we're going to add like terms. So it's negative 1 and 3 gives us 2, and the positive 2i and the positive 3i is positive 5i. Okay, pretty simple, adding just like you would do if you had to make the rules up. Okay, subtracting. Well, again, we're dealing with complex numbers. There's a real part and imaginary part. It'll be in parentheses, and the rule for subtraction in front of parentheses is to change subtraction to add the opposite. So we're going to change that minus to plus, and I'm going to change all the signs in the parentheses to the right of that negative sign. So negative 1 is positive, so I just preface it with a negative. I've changed the sign, and one way to change the sign of the second part is to simply change the operation here. So it's minus or subtraction. I'll just change it to plus. In effect, I've changed the sign of this. Now we go ahead and add like terms. The real parts added to the real parts are 7 plus negative 1 is 6. And negative 5i and positive 5i is 0i. And of course 0 times anything is 0. And then 0 plus 6 gives us the answer 6. Okay, go ahead and try this one. All right, changing this to add the opposite. We'll change this sign, and we'll change this to a plus 2, and negative 3 is negative 1. 3i, negative 3i, and positive 7i is positive 4i, and of course that's our answer. All right, now multiplying gets a little more involved than adding and subtracting. It's very direct here, but in multiplying, our example number 1, we're going to multiply two what I call just imaginary numbers. There's no real part. There's no, like, it's like 0 plus 5i, so the real part's not there. So we're multiplying two just pure imaginary numbers without a real part. Well, to multiply these, you just multiply the coefficients. We'll call 5 and -3 the coefficients, and that gave us our -15 here. And then I times I is going to be I to the second power. We are never allowed to have more than I to the first power in a simplified answer. So we go to the powers of I chart, and we find that I squared is equal to -1. So we put -1 in for I squared, and then it's -15 times -1 or +15. Okay, you do this one. Okay. Negative times negative is positive. 2 times 4 is 8, and then I times I is I squared. I squared is equal to -1. 8 times -1, -8. Okay, example number 2, we're multiplying an imaginary number times a complex number. So what we're going to do is just simply distribute this throughout this complex number. So we're going to -6i times -2, or negative times negative is positive. The real part, or the coefficient in this number, 6 times 2 is 12, and the only I that we have comes over unchanged, so we get 12i, positive 12i from multiplying those two. Now we take it over to the positive I. Negative times positive is negative. 6 times, there's a 1 in front of that, so 6 times 1 is 6. This I times this I is I squared. That squared kind of floated off on me there. Okay, and then we have -6 here times -1, which is going to be +6. And the correct order to put an answer when it's a complex number is to have the real part first. So that +6 is going to move to the front. Since 12 is positive, I write plus 12i. So +6 plus 12i. Okay, give this one a try. Okay, you probably noticed that this overgrown I here wasn't dotted, but that you might have thought it was a 1. This is actually an I. I think I had the capital I instead of the small case I when I typed this out. But nonetheless, this is an I. So -I times 3 is going to be -3i, and -I times a positive I is going to be -I squared. Okay, I squared is equal to -1 minus a negative is plus. Put it in the correct order. Real part first, plus 1 or +1, and then the -3i at the end. Okay, now we're going to look at multiplying two complex numbers. Okay, so to do this, then we're just simply going to FOIL it out, or distribute both of these through the second one. So 7 times -1, or first times first, is going to be -7. 7 times this, or the outside, these are the outside two. 7 times positive 2i is positive 14i. Now we go to this one, and we have to take the sign with it. So we have -4i times -1. That's going to be positive 4i. And then -4i times positive 2. Positive times negative is negative. 4 times 2 is 8. I times I is I squared. All right, collecting these two like terms here because they're both I to the first power, plus 18i minus 8 times, now we'll go ahead and substitute -1 in for I squared, -7 plus 18i minus 8 times -1 is positive 8. 8 and -7 will be positive 1, real part first, plus 18i, imaginary part second. 1 plus 18i. Try this one. Okay, FOILing it out. First times first gave us -12. Outside 2 times -2i, -4i. Inside positive 3i times -6, -18i. Last times last, positive 3i times -2i, -6i squared. The middle terms are like. We add them and we get -22. I squared is -1. -1 times -6 is 6. Add the 6 to the -12 and get -6 minus 22i. Okay, example number 4 is still multiplying two complex numbers, but these are a special pair, and I want you to look at both of these. And these are called complex conjugates. They're both complex numbers and they're conjugates. Conjugates just have a different sign in the middle. So this positive changes to a negative. The 6 doesn't change. It's positive. It stays positive. So we can say that the second sign changes in this binomial. And watch what happens when we multiply these. So first times first is going to be 36. And then we multiply the outside and we have negative 18i. And then we multiply the inside, and positive 3i times 6 is positive 18i. And then last times last, and that's going to be negative 9i squared. Okay, so collecting the like terms in the middle, well, negative 18i and positive 18i cancel. We have negative 9 times negative 1. We have 36 plus 9, 45. Okay, so this is equal to 45. Now what's interesting about this is that we had two complex numbers and we multiplied and we got a real number, no imaginary part to the answer. That will always happen when you multiply two complex conjugates. Okay, and the outside and the inside always cancel. And if you recognize your product as being the product of two conjugates, help yourself to a little shortcut. All you have to do is first times first and last times last, because outside and inside, when you multiply conjugates, will always be opposites and cancel. Okay? Let's try one. Okay, so when you fold it, first times first gave you 1. Outside, when we multiply, gives us negative 2i. Inside, when we multiply, gives us positive 2i. Again, we knew those were going to cancel. You could have just not done those. And then last times last, negative 4i squared. Now, one of the shortcuts I also take is that if I have a product and one of the factors is i squared, I just cross it out and change this sign. It's not hard to change a negative to a positive, so I'll change that to plus, and that's where I got 1 plus 4. If it was already plus, I would kind of mark it out and just float a negative above it. But if you have something other than just I squared, if I squared is a factor of something, you can just change the sign of that individual factor. Okay? All right. Now, dividing or changing to standard form, or even we could even say this is simplifying. Okay, so when we have fractions that have complex numbers in them, we have to simplify them. Now, the problem comes in the fact that we have an I in the denominator. Remember, we said I was equal to the square root of negative 1. And from previous lessons, we know that we're not allowed to have radicals in the denominator of a fraction. So if you can't have a radical in the denominator of a fraction, you can't have an I there either, because it's equal to the square root of negative 1. So we've got to get rid of the I in down here. Now, what we need to do, if you remember from that last problem, is if we multiply this thing by its conjugate, we will get a number that's a real number. So if we multiply by 1 plus 2i, or the conjugate of whatever this denominator is, then we'll have a denominator that's acceptable, and that's the way out of this. Multiply by the conjugate of the denominator, the complex conjugate. Okay? All right, in the numerator, we have to FOIL this out. So 5 times 1 is 5. Outside, 5 times positive 2i is positive 10i. Inside, 3i times 1 is positive 3i. And then 3i times positive 2i is going to be positive 6i squared. Okay? We'll reduce that in a minute. Let's take the shortcut now. Let's just do first times first, which is 1, and then last times last, which will be negative 4i squared. Now let's use our little shortcut for I squared factors. If it's factor something, it changes the sign. So that would be plus 4 here. It's going to change that plus 6 to minus 6. All right, let's reduce the numerator. Negative 6 and positive 5 is negative 1. Add the like terms, the i's to the first, and we get plus 13i. And that's all over 5. Okay? Now, what I'd like you to know is that because we're dealing with a complex numerator, we really can't stop here. Now, going back to some previous lessons, if we had an answer like negative 1 plus 13, say square root of 2 over 5, Well, it was acceptable for us to stop here. What we did do, though, is check to see if whether there was a common factor that would cancel with 5, remembering that you can only cancel factors, you can't cancel addends, so it would be incorrect to say if that was a 10 to just cross that 5 out and make that a 2. If this was 10 squared of 2, you can't do it. But this was okay to leave this answer right here. But what we want to do when we have a complex numerator is to separate the real part from the imaginary part. So we're going to break this into two fractions. So it's going to be negative 1 over 5. This will be the sign between the two factors, and 13 over 5i. So we can clearly see the real part and the imaginary part. This kind of answer, or this kind of expression, needs to be simplified and separate the real from the imaginary, whereas if it was any other square root, we would be satisfied with leaving it like that. Okay, you try this one and look to simplify your answer. Okay, multiplying top and bottom by the conjugate, and I hope you did not change this sign of the first thing, because conjugates you only change the second sign or the middle sign. So that negative 1 had to stay the same. There is a temptation to change that one too. Hope you didn't. Negative 1 plus 2i over negative 1 plus 2i in the numerator. 3 times negative 1 is negative 3. 3 times positive 2i is 6i. 11i times negative 1 is negative 11i. And 11i times 2i is positive 22i squared. In the denominator, we'll take the shortcut because we're multiplying conjugates. First times first, negative 1 times negative 1 is 1. And then last times last, negative times positive, negative 2 times 2 is 4. I times I is I squared. Okay? All right, so simplifying this, we'll add these like terms here. And so we got negative 3 minus 5i, and then this changed to a negative right here because it's a factor of I squared. That gives us the negative 2. Down here, this changed this to a plus, so that's where we got the 1 plus 4. Taking these two and adding the real numbers together, we get negative 25 minus 5i over 5. We can't stop there. We have to break it into real and imaginary, so it's negative 25 over 5. This sign goes between them, and then 5 over 5. And reduce 25 over 5 is 5, so we got negative 5 here, and 5 over 5 is 1. 1 disappears into the I, so it's negative 5 minus I. All right, now we're going to do one where the denominator is an imaginary number, not a complex number. So it just has the I part. And when that's the case, all we need to do is simply multiply by I over I. Okay? So doing that in the numerator, I times negative 1 is negative I. I times, this should have an I on it here, sorry. Let's add that in there. I times negative 2i is negative 2i squared over negative 2i squared. Remember, I squared changes the sign, and now we'll have 2 minus I over 2, and then we'll break that into two fractions, 2 over 2 minus I over 2, or 1 minus I over 2, or that could be written, not that it's any better or worse, as minus 1/2 I. You can take that understood 1, pull the I out to the side, and that becomes 1/2. Either answer is fine. Try this one. Okay, well, multiplying by I over I in the numerator, I times positive 3, positive 3i, I times negative 4i, negative 4i squared. In the denominator, I times 5i, 5i squared. Okay, I squared changes the sign here, I squared changes the sign here. So we get the positive 4, putting it in the correct order. Of course, the 4 should go front, so we have positive 4 over negative 5, or negative 4/5, and then we have positive 3 over negative 5, or minus 3/5 I. Okay, now the next thing we're talking about is plotting complex numbers. To plot a graph or graph a complex number, we need to make a complex number plane where the x-axis becomes the real axis, and we call it R, and the y-axis becomes the imaginary axis. So instead of y up here, we have I. So if we want to graph 3 minus 4i, it's simply plotting a point at what would be 3 negative 4. So we go over 3 on the real, and then we go down 4, and that point would represent this complex number 3 minus 4i. Okay, you try this, graph negative 2 plus 3i. Okay, hopefully you found the point to be right about there. Again, we'll go -2 for our real part, and then up 3 on the y-axis up to here. All right, next screen. All right, now we're going to talk about finding the absolute value. Okay, so to find the absolute value of a complex number, it's very similar to what we did with real numbers. If we were asked to find the absolute value, or the way we described finding the absolute value of, say, -3 was, we showed you a number line and we found -3 there, 0, 1, 2, -3, and we said it was the distance of this line right here, or distance from 0. Well, with complex numbers, the absolute value kind of follows the same way. It is the distance from the origin. So here we have 4, +3 marked here, and the distance that this point is from the origin is whatever this line is right here, the length of this line. Now, what I've tried to illustrate here is that the length of that line is really the hypotenuse of a right triangle that we have here, whose legs are 3 and 4. Okay, and by the Pythagorean theorem, we can find the length of this line, which will be the absolute value of this, okay, by squaring 4 and squaring 3, so we get 16 and 9, adding those together. 25 is equal to the square root of this, or excuse me, x squared, and then we take the square root of both sides here, and we get x is equal to 5. Now, I know in the past we've said if you take the square root of both sides, you're supposed to do plus or minus, but in this case, because we're talking about a physical distance, negative doesn't make any sense, so we only put in the positive one, so the answer to this is 5. Okay? You try to find the absolute value of -3 plus 2i. Okay? Finding -3, 2i, go from the origin, go over 3 and up 2 on the I. And that distance is right here. Okay, so we want to look at the triangle, the right triangle, whose height, one leg is 2 and the other leg is 3. Using a Pythagorean theorem, it's going to be 2 squared plus 3 squared equals x squared, or c squared, some put c. So we have 4 plus 9 is equal to x squared. 13 is equal to x squared. Take the square root of both sides, and x is equal to the square root of 13. So that's the absolute value. It's equal to the square root of 13. Now, let me say this. It's not necessary for you to graph it to find the absolute value. You can go ahead and just pick the numbers out and square them, and take the square root, and that will work just fine. All right, that ends the lesson. Thanks for watching.